Share my screen. Okay, can you all see my screen?
Yes, sir.
Yeah. Oh, okay. So we will continue with source localization. We'll wrap up the beam forming part and then move on to forms of connectivity analysis. So there are now two classes remaining today, and so Friday is a holiday. But is it okay if we have the class on Friday, or so we'll have to do it on either Friday or Saturday or Sunday because next week onwards interviews are starting. So is Friday 9 o'clock fine with everyone? Um, can some of you say something, either yes or no?
Friday will be okay, sir.
Okay. Is there anyone who's not okay with Friday? Okay. So in that case, let's do the final class on Friday and then we'll be done with the coursework part of this course. All right. So a quick recap. Um, we we very briefly talked about parametric models, but mainly we focused on the non-parametric distributed models in which dipoles are assumed to be at a fixed location and you know different orientation as well. So if there are 1,000 dipoles, you would have 3,000 different dipoles, each pointing in x, y, and z directions. And then all you have to do is just find out what the magnitudes are. Okay, so V is equal to GD. G is a fat matrix where the number of electrodes are much smaller than the number of dipoles. And all you have to do is find out what the magnitudes of these dipoles are to solve the inverse problem. Okay, and because it's a highly under constrained problem, we have to apply additional constraints. And we used one constraint, which is the minimum norm solution, in which we assume that the L2 norm of D is as small as possible. Okay, and if you put that constraint, the solution is given by this formula, which can be pre-computed because you know what G is. So you can compute G transpose, GG transpose inverse upfront and store that. And then whenever I give you a 64 cross 1 voltage trace, you will get a 10,000 cross 1 dipole vector. And if I give you a time series of voltage, you will get a time series of dipoles. Okay. So this one we solved. This one mathematically was not that involved. However, there are, this is the simplest one that people use, and the more involved techniques require a fair bit of linear algebra. So I didn't actually solve those things. I just gave you what the solutions are. And intuitively, they all have this sort of a form with a few additional things added here and there, which I mainly described without really proving. I just gave sort of a intuitive feel for this. So one thing is that you want to, not penalize deep sources because deeper sources will have a smaller contribution in the scalp space. So if you're looking at a minimum norm solution, you will never end up choosing a deep source because deeper sources will have to have a large um, magnitude in order to be visible at the sensor level. So you can pre-multiply the D vector by some matrix P, and instead of minimizing D, you minimize WD. This is some sort of a normalization that is done, and that's called a weighted minimum norm solution. Um, And then there is, this other assumption that is often used, that your sources are sort of not very pinpointed. They are usually distributed, so that you don't see much of a difference between one part of the brain and its neighbor, because they get similar inputs from other areas and so on. So you could, instead of minimizing the norm of D, you can minimize the Laplacian of D. And this is called Loretta. Loretta has one matrix to apply a Laplacian, another one which normalizes its columns. So it has this form. The other form I'll show you in the next slide. But the general form, when you also have noise in the system, is that you try to minimize this. Okay, earlier we were just minimizing L of D, where L is some sort of a constraint that is put. We could talk about the L2 norm of D, which would then give me the minimum norm solution. But the general form, you try to minimize this. Note that GD minus V is no longer 0. It's actually your estimate of the noise in the system. Okay, so you want to minimize the noise as well as some regularized form of this cost function. And then if you have this as the function that you minimize, your solution, the minimum norm solution, becomes this. Okay, it's very similar to your previous one. It just has this alpha in term, which is because now you are, not forming the exact solution, but a slightly modified one. And the weighted minimum norm solution becomes this. This is stuff that I didn't prove. I told you where to find the proof. It's a bit involved. We don't have so many classes to do this properly. But you are welcome to read this up and, if you're interested, try to figure this out. Okay, so this is the weighted minimum norm solution. Note that in this case also, you can pre-compute this entire matrix, so that whenever I give you V, you can find this out. Okay, so this entire computation doesn't need any knowledge of V. You just need knowledge of your head model, the source model, and the electrode location. And for W, you just need to have some sort of a biophysical understanding of how much you want to weight each source depending on its position. Okay, and in this formulation, Loretta becomes this. Here you have two matrices, this delta, which is the Laplacian operator, and B is a diagonal matrix, which normalizes the column of G, thereby not penalizing the deeper sources compared to the superficial ones. And the Loretta solution becomes this. And in general, if you assume that uh, um, your electrodes and the dipoles are not independent of each other, but they have some covariance between them, given by these covariance matrices C and R. C for the electrodes, R for the dipoles. Your minimum norm solution in this more general case becomes this. Okay, notice that when R and C are both identity matrices, which is when the variances are the same and covariance is 0, then this would reduce to this one. Okay. All right. So that's that as far as the non-parametric part is concerned. I just summarized what we had done in the previous class. Is there any question on this, or can I move on and talk about well, I'll get to beam forming, but before that, I'll briefly tell you something else also. Is there any question on this, or are people more or less okay?
I have a small doubt regarding the deep sources. Shall I ask now or later in the class? After the class?
Um, okay, let me finish source localization and then you can ask, because maybe it will get answered in the next few slides. Okay, so let me move on then. and tell you a little bit about some of the issues with L2 norm solutions. And this is where we get some intuitive feel for L2 versus L1 norm as well. Okay, so here's an idea, here's an example where you have two sources which are separated by 1 millimeter. Okay, and you have another solution in which there's a single source which has twice the magnitude. Okay, and suppose both these sources explain the data equally well. And intuitively speaking, you can think that they are sort of equivalent solutions. But let's ask whether if I impose an L2 norm and say my solution should have the minimum L2 norm, which of the two should I end up picking? So source 1, which is this one, has an L2 norm of root of 1 square plus 1 square, which is root of 2. What about the second one? It's root of 2 square, right? Which is 2. So source 1 has a smaller L2 norm than source 2. So in general, if I impose a minimum norm solution, I will always have a solution in which the dipole is broken up into. So here you can think of the first solution as a bigger dipole broken up into smaller dipoles. And this always has a smaller L2 norm. So L2 norm always, if you minimize the L2 norm, it will always give you a very distributed solution. If you have one dipole in the brain and you get some voltage distribution, and you say, okay, find me a solution which will have minimum norm, you will never recover that one dipole back. You will get tons of very small dipoles scattered nearby. So that's not good. You're never getting a crisp solution. So actually changing this norm from L2 to L1 solves this problem, can solve this problem. So here the L1 norm is 2 in both cases. It's mod of 1 plus mod of 1, which is 2 here, and mod of 2 here, which is also 2. So both have the same L1 norm, even though the L2 norm is smaller for this compared to that. Okay, so there are lots of algorithms that try to minimize the L1 norm instead of L2 norm. And this gives a very sparse solution, a sparser solution than the L2 norm. So here's a nice graphical way which I got from this lecture here, which explains this concept. And the idea here is that if I say that I want to have an L1 norm, how does the solution space look like? Okay, so suppose, okay, so here your W1 and W2 are the weights of two dipoles. In a higher dimensional space, let's say a 10,000 dimensional space, if you consider there are 10,000 dipoles, this would be some sort of a plane on a 10,000 dimensional space, but let's just consider a two-dimensional space like this one. So your yeah. So if I say that I am trying to have an L1 norm, so the L1 norm is just given by this sort of a equal to some constant. So if I ask you mod x plus mod y equal to 1, let's plot this. This is actually a question that I ask in another course that I teach in calculus. The solution is going to be a diamond like this. Okay, so where is this coming from? When x plus y equal to 1, in the positive, this positive side, Mod of x is just x because x is positive, mod of y is just y. So you're solving x plus y equal to 1, which is this line, like that. Okay, but it's only for the first quadrant. In this quadrant, y is positive, but x is negative, so it becomes minus x plus y equal to 1. That's this here. And this thing, y is equal to 1 plus x, is this. Okay, and likewise, if you do the other two quadrants, it will become something like that. Okay, so your L1 constraint, when I say my L1 norm should be some value, okay, that means it is asking your the weights here W1 and W2 along these axes, a solution that lies on this diamond here. When I say this plus that, which should be something else, if I say it's 2, it's going to be now a bigger diamond. If it's 0.5, it's going to be a smaller diamond, and so on. L2 constraint, where you put a square, is a circle. Okay, and suppose the likelihood is given by this. This is the likelihood that W1 and W2 are taking some value. So it's, this is like a contour plot. And the solution lies where this contour plot and this constraint sort of, intersect. So if you have a diamond-like shape, you will always intersect in a point like this, in which one of these axes is actually 0. Okay, so for an L1 norm, you tend to intersect either on this axis or on that axis. If you put an L2 norm, you will always intersect because it sort of sticks out like this, where both are non-zero. So this gives a distributed solution. This gives a sparse solution. Okay, this is a very sort of loosely defined intuitive way of thinking about sparsity. But remember, when I have this here, G is a extremely fat matrix, 10,000 cross 64. Sorry, 64 cross 10,000. And D here is also a 10,000 cross 1 matrix. Now you really don't want 10,000 non-zero entries here. You will solve it, but why have so many dipoles? It just complicates the interpretation. It's much easier if you have a few localized dipoles, which means you want a sparse solution where a few dipoles located at strategic points can actually give you V back rather than having so many different dipoles. So this sparsity can be imposed by using the L1 norm instead of L2 norm. And it's implemented by methods such as this minimum current estimate, or MCE, is a variant of your minimum norm estimate. So just to give an example, so you can have these are your actual dipoles. So this is all simulation. So there are 3 dipoles. From these 3 dipoles, if you solve the forward model, you get a voltage distribution that looks like this in the noiseless case and this in the noisy case. And then you say, okay, from this data now, let me recover back my dipoles. Now, if you use an MNE, or a minimum norm solution, it gives a smooth solution which looks like this. See, it's all over the place. It's not localized to just 3 locations. It's all over the place. And unfortunately, that is the case because L2 norms tend to give a distributed solution. Now you could say, okay, let me use L1 minimization. And now you can see there are just these small dipoles of very high magnitude, which are your solutions. This is not also a great solution, but you can find a mix of these two. So you can say my cost function is the L1 norm plus some parameter here plus the L2 norm, and that gives you the proper solution that you see here. Okay, of course, it depends on what this is, and these things tend to work very well with simulated data but fall apart when you have real data. But nonetheless, the idea here should be clear that you are trading off sparsity and smoothness and trying to get at a solution which incorporates both. So this is a mixed norm penalty. Okay.
When we get this localized solutions, so here able to get the three sources like localized
Yeah, in the
sources.
both in the mixed norm, you are getting the 3 back.
Yes. So basically, for this, is it through the electrodes? Means how many electrodes we plugged in that decides how many sources we'll get localized sources, or what decides the number of
No, no, no,
sources?
no, no. So these 3 dipoles, so this is all simulation. You put
Okay.
these 3 dipoles, 1, 2, 3. Okay, so you put these 3 dipoles and then you use your forward model to get this data. This is now sensor data. Now from the sensor data, you're asking, let me find out where the sources are. So now you are solving the inverse problem to get back your sources. Okay, so you see the G matrix is already defined because you have the you have some head model, you have some source model, and you have some electrode locations. So you have already done D. So now, so this fat matrix now, and you are specifying a particular type of D. Okay, you are saying I've got just 3 elements that are non-zero. I guess 3 cross 3 because each one will have 3 3 dimensions. So out of my 10,000 potential dipoles, I have got only 3 dipoles. You plug these values in and it will give you a V. That V is here. Now you say, okay, given this V, find D. And let's see this D, whether it matches with the D that I put in earlier. These 3 values correspond to the 3 dipoles that we have. 3 entries for each dipole, 1 for each x, y, and z direction. Okay, so I first had a particular D for these 3 dipoles. From there, using the forward model, I generated V, both G times D, which is here, and G times D plus some N, which is here. And now, given V and the knowledge of G, I'm trying to estimate D back, which is my inverse problem. And if I do an L2 normalization, minimization, I get this distributed matrix where this entire brain is lighting up. If I do L1, it's just way too sparse. You just get very small solution because it just tries to find a very sparse solution. But when I do a mixed norm, I'm getting both this and that. I'm getting the sources, these 3, which pretty much match where my original dipoles. Okay.
This seems then when we start with estimation of D, it looks like an iterative problem too.
It's
Can be solved
what?
iteratively.
What?
So
What?
I said that when we have this D, you said that we assume 3 values of three elements of D and put rest 0, and then
Yeah.
we begin D and we start estimating everything.
Yeah, G is known. G is already known.
Moon. So the basic idea I'm saying that this becomes to estimate D properly, it becomes an iterative problem, isn't it?
Why is it iterative? There's no iteration here. None of these are iterative problems.
No, 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 no. This is not iterative. This is direct. So I'm saying when you have say if you assume 3 elements of D, okay, and then you calculate V and how much it is deviating from its original value, and then again you iterate the elements
No,
of
no,
V
no,
and
no. Here, all these guys are saying that if you use a mixed norm penalty, you
Mhm.
will end up getting sources that match with the original ones. You're not sort of optimizing it to find this. They are just saying that if you use the mixed norm, you are going to chances are you'll end up getting sources that reflect the true sources that were there. But you're not optimizing this. You're not saying that, oh, if my sources are somewhere else, let me do this again. You're not doing that in this case. All you are
okay,
saying is that a mixed norm tends to give solutions that are, you know, closer to the actual solutions, but you're not optimizing here.
okay,
Okay, all of these are direct solutions like these. This whole thing is direct. There's no iteration. You know what G is, you know what this is. You assume some value of alpha and you get a solution. Okay.
okay.
All right. So now let's talk about another class of solutions called beamformers. So the idea of a beamformer is quite straightforward. In fact, in this lecture, half of it is given by Hoffe, another half is given by Nolte. And you should really listen to Nolte's part because he explains this very beautifully. In fact, the way I'm explaining right now is just pretty much, taken from the way he has explained. So let's go through this. It's another class of solutions, beamformers. Here you are not assuming that the dipoles are all over the brain. Here instead, you say I'm going to pick a spot, some location R dipole, and I'm going to try to estimate the magnitude of the dipole here based on the sensor data. Okay, so how do I do this? Now think about this in the inverse way. This is just to give an intuitive idea. So suppose you've got a source here, ST, and you've got two sensors, X1 and X2. And I say that let me find some linear combination of my sensors which give me a good estimate of the source at this location. Okay. So I'm essentially looking at a weight vector, which I'm going to multiply with my sensor vector. So x1, x2, whatever. This will become W is some column vector. So this becomes a row vector. So this is just one entry. W transpose X is one entry. Okay. So this thing should approximate my source at a particular location. Now, if I change my location, then obviously this weight vector is going to change. But the idea is my weight vector should be such that it approximates the source at a particular location. Okay, this is just half of the story. There's more to it, but this is the starting point. So suppose there's a trivial case where x1 is equal to s and x2 is also equal to s. So somehow both of these sensors are just catching the source perfectly. This is a hypothetical example. Then how do I reconstruct S as a linear combination of x1 and x2? Now in this case, there are infinitely many perfect solutions. I can say S is just x1. That is also correct because x1 is just S. I could say S is just x2. I could say I'll just average them. or I will take alpha times x1 plus 1 minus alpha times x2. These are all correct solutions. They will all give me S back. They are all linear combinations of x1 and x2. Correct? But now let's think of a more involved solution where you are looking at noisy versions of S. So x1 is some S, but you have added some noise. X2 is also S plus some noise. Now, intuitively, what would you do to get an estimate of S given this noisy situation? Now, intuitively, you would say, I'm going to weight the electrode more if it is less noisy, and I'm going to apply a smaller weight if it is very noisy. It's like you penalize it for being noisy. So if you don't trust that signal, you will give it a small weightage. Right? So here are some examples. If sigma 1, which is the noise level, is 0, then I just choose S as x1 because it's just S in this case. Of course, I need to know what the noise levels are, which I may not know, but for the time being, let's just assume I know the noise level. So if sigma 1 is noiseless, then S will be just sigma x1. If the noise is the same, I'll take the average. The noise level sigma 1 and sigma 2 are the same, then I'll take the average. If sigma 1 is twice of sigma 2, which means electrode 1 is twice as noisy, then I'm going to have a solution that looks like this. You might be wondering where this is coming from. This is the noise level. So this the variance is the square of that. So I'm just dividing by now the variance total variance is 1 plus 4, which is 5, and now the relative ratio depends on the noise level. The second electrode, because sigma is half of that, is now 4 times as much weighted as this one. Okay, so these coefficients can be thought of like a filter. Each one is multiplied with some weight vector, W1 x1 plus W2 x2 and so on. So it's actually a computation that looks like this, where W is a column vector, so it's a row vector like that, where W should depend on the noise of each electrode. Okay, that's where the term beamformer comes about, but there's more here. So what is a beamformer? It's a spatial filter, or you can think of it as a virtual sensor, because I'm looking at a linear combination of the real sensors. The advantage is that you don't need to assume the dipole locations a priori. If you give a dipole location, it will give you a solution, a set of weight vectors to find the dipole at a particular location. So unlike a previous case where I told you that, okay, dipoles are all over the place here, and dipoles are all over the place, and then I find an overall solution by making a fat matrix G. Here, I'm not doing that. I'm just asking what's the dipole at a particular location, and I'm going to find a way to do that from the sensor data. And the idea here is as follows. This is where the full picture comes about. The basic idea of a beamformer is that a beamformer tries to reconstruct the contribution of a single location from the measured field. So the idea is that I need to have a spatial filter which blocks the contribution of all sources that are not at this location. So my weight vector should be such that I'm able to reconstruct the source at a particular location perfectly, but the weight vector is also going to give a zero value for any other location. Think about this. This is not a non-trivial concept. I've got sources from many locations, and the contribution at the sensor level is from all of them. But I want to find a weight vector or a spatial filter, which when I apply to the sensor data, will reconstruct the source at a particular location, but cancel the sources everywhere else, so that I get a true reflection of what the source is at a particular location. Okay, so let me read this out. The output YT of a beamformer is a product of a 3 cross n spatial matrix. This 3 comes about just because at each location I've got 3 dipoles, right? One pointing in the X, one pointing in Y, one pointing in Z direction. And I'm going to multiply it with my n cross 1 voltage sensor data. Here M is like V, previously used V. So the output Y is just a 3 cross 1 vector. It's just the value along the 3 dimensions at a particular location. But it has to satisfy this condition. So if I give you a location, R depth, my spatial filter will depend on this location, and it has to follow this constraint that the weight vector at R depth multiplied by the gain field matrix is identity if R is very close to R depth. So it's reconstructing my dipole at R depth, but it's zero everywhere else. Okay, this is a complicated concept, so maybe uh, just think about this carefully. What is happening? I've got a location Q naught. This I pre-specify. This is the same as R dip. Okay, if I put a dipole there, I'll get some sensor data, sensor space, and now I want to find a weight vector which will reconstruct this dipole at Q0. But the weight vector is also such that a dipole at any other location will get cancelled out. So it's going to have a spatial filter that looks like this. This is now the location space. It reconstructs it perfectly. This is a perfect ideal filter, which is not possible in real life, but we won't try to approximate this. Okay, so a beamformer essentially gives me a weight vector, and when I apply this weight vector to the data, it gives me the source at that location. So if I can estimate that weight vector for any given location, then I apply it to the data and it gives me the source. That's it. That's a beamformer. Okay, it's like a beam that is being formed. That's it's a cool name that comes about because here you have the sensor space and the linear combinations can be thought of as weights. So it's like um, forming a virtual sensor, which is like the source here, being a beamformer. I mean, it's an approximate way of thinking about it. But it's a spatial filter that blocks contribution from all sources other than where the desired location is. Okay, don't worry about whether we can compute this properly or not. Obviously, we can't because we only have 64 sensors and potentially a much larger number of dipoles. So we will approximate this, but nonetheless, the concept is what I just mentioned. Okay. So let's see how it is done in a real real data set. The problem with the real data set is that I don't know what the noise level is. I don't know what the noise level is. So how do I actually get an estimate of the noise? Now, the idea that, so this is what is called the LCMV beamformer, the linearly constrained minimum variance beamformer. Here, the idea is that I can measure the sensor data. I don't know what the source data is, but the noise in the sensor data, the variance in the sensor data is the sum of the noise in the source and the noise, the variance of the source and the variance of the noise, assuming that the source and the noise are independent of each other. But this is a fixed thing. Okay, so an estimate of the noise can be obtained by looking at the variance in the sensor data. So you could try to minimize the noise in the sensor data, which will minimize the noise in the the variance of the noise as well. Okay, so the LCMV problem statement becomes as follows. You estimate the covariance matrix from the data. Y is the data. Okay, sorry, Y is not the data. Data is M. Sorry about that. Y is W transpose M, which is your estimate of this source. This thing here. YT, it's your estimate of the output. It's a 3x1 matrix here. Okay. Now you want to find the covariance matrix of Y, which is just this. Because Y is W transpose M, YY transpose is W transpose MM transpose W. So its covariance matrix is just given by this. CM is what you can compute because you have access to the data. This data M is your voltage vector, sensor data. You don't know what W is though. So you only know what CM is. However, you can put a constraint on W and say that I want a W vector such that this condition is satisfied, that the W vector computed at RDEP multiplied by the gain field matrix at RDEP is the identity matrix, which is this condition here, this condition in the vector form. And then you try to minimize the trace of this. The trace is just your sum of these diagonal entries, which is the total variance of this. Okay, so you are trying to now find a W vector which minimizes the trace subject to this condition where Cy is given by this. And if you have this problem statement, you can use Lagrangian multipliers to actually get a solution which looks like this. This is your weight vector. From the data now, given your data, you can find the covariance matrix. You know what G is, so you can compute G at RDEP and you can actually compute the whole thing. The solution, weight vector, depends on the covariance matrix. But once you have the data, W matrix, once I give you M, you can tell me what the source is. It's just W transpose M. Like this. This is the beamformer. Does that make sense? Either say yes or no so that I know whether I can move on or not. Um, guys, is this fine or?
Well, I could not understand one thing, that we have C and we have W. So G is already known. So which is we are computing first, means which we are obtaining from previous data, and we are obtaining W. This is fine, but I'm just little confused.
Okay, which part is confusing? So M is your sensor data. From this,
Hmm.
you can compute your covariance matrix.
Okay.
Once you have the covariance matrix, you already know what G is. So G
Yeah.
at any location is this. So then you know this entire W. And once you have this, you can then find the sources as W transpose M.
Okay. Okay.
Okay, and this W vector is going to be different for each location because this G at R dip is going to vary. So unlike previous case, I can just ask, tell me the source here or tell me the source here. I don't need to know what is going on at the other location. My beamformer actually should take care of all of this. So I can just ask, tell me the source at this location. So once I give you this location, I can find G at R dip, and given the data here, M vector, I can find its covariance matrix, this, and my W weight vector is just this whole thing. This entire thing can be computed. And then I multiply it with my voltage vector to get my source at that location. That's it. That's how a beamformer is working. Remember, that's what it's doing. It's finding a weighted average of the sensor data such that you are able to reconstruct it properly at one location, but all these contribution from all the other locations get filtered out. That constraint is put here, and the noise level, minimization of noise, this earlier idea that I was mentioning here, is put here. You're minimizing the trace. Okay. Now, one nice thing about beamformer is, well, it has lots of nice things. One particularly nice thing, the reason why I actually talked about this in more detail, is that it has a very nice representation in the frequency domain as well. Because you have a very nice way of thinking about the signal variance and the covariance in the frequency domain. So instead of signal variance, we can use the power, and instead of the covariance matrix, we can use the cross spectrum. So here, if you replace the Cm, instead of here, it's a function of time, right? Um, all of these are functions of time, but the exact equivalent representation in the frequency domain is just the cross spectrum, the product of the spectra, whereby now you have the power along the diagonals, and these would be your cross spectrum entries. So you could actually solve this whole thing in the frequency domain, and that is what is called DICS, dynamic imaging of coherent sources. And the reason why this is important is now because I can ask, where are the gamma sources in the brain? So I could have done it in this domain also. I could actually solve it in the time domain. So then I get a source vector, which is a time, which is a function of time. So in my brain, I can find out whatever number of sources I have and have a time series there, and then take the Fourier transform and say how 40 hertz is distributed and 80 hertz is distributed and so on. So I could solve it in the time domain using LCMV and then take the Fourier transform. But I could actually do it directly in the frequency domain as well. by instead of using the covariance matrix, I use the cross spectrum. Okay, and then I can actually answer the question that I started out with, as that I am seeing gamma in the brain. Where are the sources? So the solution is that you choose a head model. You can create a source model. You compute the gain field matrix knowing the electrode location. Once you have the gain field matrix, in this case, you use DICS and say, tell me the sources at 40 Hertz or wherever your gamma peak is. And you will find a solution that looks like this. The source localization code should be able to give you this. And you can see that the sources are nicely localized in the occipital area. This is the eye here. This is the back of the brain. This is where I look from the top. Sources are nicely located in the back of the brain. So I've actually solved the question that I started out with. Remember, I started out by saying I'm seeing some gamma in the sensor space. Tell me where the sources are. This is the solution. Now I could have used Loretta also. I could have used LCMV also. I could have used, any of these other methods. They would have all given me a time series back, and I could have computed the Fourier transform and then computed it that way. DICS is a method that allows me to look at it directly. So it's very popular in people who study gamma oscillations and all that. So that's why I wanted to talk about that. Okay. Okay, now I can take questions. No point starting the connectivity analysis in this class. So I'm going to talk about 4 or 5 different methods, and it may spill over in the next class. So is it okay if I take a slightly longer class so that we finish on Friday? I'll try to, we have done coherence and the remaining ones are just slight variants of that. It won't take too long. So maybe in 1.5 hours, I'll be able to wrap up everything. Do you guys have, does anybody have a class on at 10 o'clock? Okay, if you don't say yes, I'm going to assume there is no class. Okay, so we'll finish off on Friday at 9. It may spill over. I'll try to be as fast as possible. Hopefully in 1.5 hours, we'll finish everything and we'll be done with the course. Okay. All right. So now I'm done with the source local. If there are any questions, please ask. Otherwise, the class is over. I'll stop recording now. Srishti, did you have a question?
No,